thermal expansion. You now have the rod, you heat it up, without restraint, you will do the free extension. This is what we call free thermal expansion. This free thermal expansion is very simple to calculate. This is the starting length times the thermal expansion coefficient times the temperature rise. So one of the important definitions here is you have the cool rod. Okay, if you now heat it up, if I do the exaggerations. So this starting length, okay, once heated up, you have this extra length. This extra length is not caused by any force. It's simply heating. Okay? So you can now define thermal strength. Okay? This is what you call thermally induced strength. Okay? On top of that, you want to further define it. So you can say that how much is strain per unit temperature rise. Okay? In this case, this is the thermal strength divided by the temperature rise. So what is the unit for this CTE? This is now having a unit of strain divided by temperature. Okay? So if you are not familiar with this, then we define the length chain. These are some definitions. So this is the first thing is your thermal strain. Mark this delta as the expansion due to temperature divided by starting length. And then here you also define about coefficients of thermal expansion. Okay. Divided by the temperature rise. Just a recap, in case you forget your physics. Okay, but your physics don't tell you that you are subjected to combined loading. You will not just be heated, you will be cooled, you will be compressed. Okay? So what is the total extension here? Okay? After the free thermal expansion, if you subject the rod to force, Hooke's law still remain valid. Then your total expansion is contributed by two parts. The first contribution is coming from free expansions. The second part is coming from Hooke's law, force divided by the stiffness. So the hot rod was being pulled by force F. Okay? So this is the graph to illustrate the point. Length increase with temperature rise. Okay? And then how about the force requirement to achieve the same extension? You can see here, if I'm going to pull to obtain the same amount of extension without hitting, I'm going to pull a lot more. But in the presence of free thermal expansion, I pull a bit, then you feel like a gap already. Okay? The other way of understanding this is if there is a free extension due to heating, okay, but I block it from extension, how much the force, how much the mechanical force do I need to stop the extension? It is going to K times the thermal expansion. So this is what we call the block force. Okay? This is what we call the block force. Okay? So from here you already can write your finite element. Okay? So many of you, if you don't have this idea about block force, then you are not able to write finite element. Okay? So in a way, if you now look at the graph here, what is the effect of temperature? Okay? At the reference temperature, if this is the Hooke's law, you need the increase in the force will lead you to increase in the extension. But because of the heating, even the force remain the same, but the extension increase. So what's the first? How do we write the finite element? By this structural understanding. Okay, let's see. Okay. So let's see what's the effect of the thermal expansion. If you now consider a cold rock, you heat it up, then it has the elongation due to thermal expansion, delta LT. Okay? So what is the force applied there? Okay? So the actual mechanical force requirement here is the final elongation minus the thermal strength. Okay? How about the left end? Left end, if right end is fixed, the elongation go backward, opposite to the force and displacement direction. So how much? The spring force here? The spring force is going to be U1 minus U2 plus the thermal expansions. Then by combining these, then we're going to write the finite element. Okay. Okay. If you find this is confusing, then we do it step by step. Okay. Yeah. You got to try out. Okay. The reason this part is included is many of you don't know how to handle it at the same time. Okay, because you are so much engrossed in mathematics that you forget about the physics or mechanics. Okay, that's why we have to spend time doing this analysis. Sorry to tell, in exam, almost half of your senior don't able to write it. Okay, if the rod is inclined, okay, 90 degrees. 45 degrees. Okay, they do not know the direction of the thermal force. Okay? So make sure you derive it. Okay? This is a cold rod. Okay? Okay? And now the displacement here is U1, U2. Okay? It may be subjected to forces F1, F2. Imagine if this is fixed. Okay? I could possibly have the elongation due to the mechanical means, but I will also have extra elongation due to the thermal expansion. So looking at here, how do I write the force balance? Okay, this is rightward positive. F2 is definitely positive because it's pointed rightward. How about the spring force? The spring force must be K times the extension. Any extension will be accompanied by a backward force. Okay? How much the extension due to mechanical means? Okay, and to right hand mechanical means. Okay, I have not two moving forward. If the back was fixed, this is U2 minus 0. But the left hand wasn't fixed. Okay, so this is U2 minus U1. Okay, so that is pure mechanical extension or not? No. You have to subtract the thermal elongation, thermal expansion. Okay. So in this way, how do you write your first equation? The first equation is F2 is equal to your K U1, is it? No. Minus K U1. No, is it? Oh, let's see. No, it's a plus, is it? Minus. Okay. Okay, I move it to the other side. So this is written to be equal. Okay. So this is minus Ku1 plus Ku2. Okay. This side I have my minus K delta LT. Okay, but I don't want to keep it here. I want to move it to the opposite side. This is K delta LT plus the mechanical force. So how do I understand this equation? From the viewpoint of force, external force is equal to elastic force. Okay? The effect of thermal expansion is you are on the right hand side, you are being pulled by an equivalent force of K delta LT. This is what we call the equivalent thermal force. Okay? On the right hand side. And then next, for the same rod, if I now fix it on the right hand side, my viewpoint is all about the left hand. You have your F1, you have your U1. Okay? Yeah, due to the rightward force, you're supposed to have a compression. Okay? But because of the hitting, you end up have the elongation. Okay? This amount of elongation is with reference to your starting length. So what is that the force summation here? Okay. Here you have to put the force sign of not 1 is equal to 0. F2, F1 is forward positive. Okay. If you are subjected to, if you are compressing this rod, you are subjected to a spring force. How much is the compression? K times the compression. Okay? Due to mechanical means. So this amount is U1 minus U2. Okay? But supposingly, if it were longer, this compression is more, then you have delta LT. You get the point? So with this, now you can write your expressions to be equal. Then you have your F1 is equal to K U1 minus K U2 plus K delta LT. In this case, I want to move this term to the left hand side. This becomes minus K delta LT plus. So this is minus thermal induced force. Okay? So how to read this? On the left hand side, the force is rightward. But because of the right end is fixed, the elongations go left. So the thermally induced force are supposed to go left. So that's why it's negative. Okay, and now you can do the combination of two equations. Okay, so how do you write this equation? This is now become Ku1 minus Ku2 is equal to F1 minus K delta LT. This is the first equation. How about second equation? Second equation is minus Ku1 plus Ku2 is equal to F2 plus KL delta T. Okay? So with this, now you can rearrange them into the matrix and vector form. force term, I divide them into two terms. One due to mechanical external force, and the other due to the thermal induced force. Okay, that's the equivalent. So you have A minus A minus A, A. Okay? So this is what you learned about simple rod expansion. If you now have an inclined rod, how do you handle it? You have the inclined rod. How does the expansion go? Expansion goes this way. So the effective expansion force, the thermally induced expansion force is K delta L. Okay? So that force, you got to reduce them into XY component. Okay? So don't just handle this as a mathematical problem, numerical problem. You really have to know the mechanics. Okay? So yeah. So ANSYS or finite element is a tool, but you have to go back to the basic. It must be validated against the mechanics or structural analysis. Yeah. Of course, in software, you probably do not need to handle the direction. Okay? But in reality, you have to handle that and you have to check it. Okay? Sometimes software has a bug. It simply doesn't tell you the right forms. Okay? So you really have to know how to handle it. So in this case, in the analysis, you have the FPX, so FP cosine theta, FPY, equal to FP sin theta. Okay? So your geometry, you have to draw them. Okay? So with this, now this is the first time we modify the Hooke's law to include the thermal expansion. Okay? Thermal expansion is equivalent to the two tension force. Okay? And then divided by the stiffness. From these two equations, we already managed to write these two. Okay? So, in the end, okay, yeah, be careful. This one, the direction should be, you should be mindful. Is it positive or negative? Depending how you define not one and not two. Okay? Here could be something, let me see, is it right? F1. Is it right? Yeah, F2 should be positive. It is on the right hand side. Okay? So please go and check. Okay, is the direction right or wrong? Okay? See, yeah? fixed. 11 fixed equal U2. So the total extensions, let me see here, the total extensions is more, so we got to do the subtractions, okay? And then later, when you move it to the left hand side, it's going to be positive. And then this one, this is the compressions, okay? It's moving opposite, so you add up, okay? So, yeah, the sign look correct here. Yeah. Right here. F1, okay, then this is top one is minus, okay, and then bottom one is positive. Okay. So anyway, it's going to be extension. Extension should be positive. Okay. And then next, after you learn about Hooke's law, then we're going to use your structural analysis. How are you going to handle the same things but by different formulations? Okay, we introduce you the idea about thermal strength. And the total strain is equal to mechanical strength plus thermal strength. Okay? So in this case, how much is the mechanical stress? The mechanical stress is then the net mechanical strain. Net mechanical strain is total strain minus the thermal strain times Young modulus. With this, now we can define the total potential energy in the hot rod. In this case, the total potential energy can be expressed as the elastic energy storage minus the work done. So in this case, the mechanical stress multiplied with mechanical strength in the calculation of strain energy. So the contribution by thermal expansion wouldn't do any work. Okay? So this expansion will then stress is strain, net strain times Young modulus. So this would end up with Young modulus times the net strain square. Net strain square is total strain square minus 2 times the total strain times thermal strain plus the thermal strain square. Okay? And now you're going to do the volume integrations to find this energy. This is the volume is area times the length. Okay. How about the work done? Negative work done minus the work done. Okay, it remains the same definition. The positive work done is defined as the force multiplied the displacement in the same directions. At the not 1 and not 2.